stats and mechanics. We just got to get on with it, haven't we? So I've got Edexcel paper 3 from June 2018, which obviously is statistics and mechanics. Now, I've not seen these questions before because I'd rather not just reel off kind of pre-built solutions for you. I'd rather you actually see me doing them in the flesh, because then you'll see the thought processes I go through. And if I mess up, that's a good thing, right? Because people mess up in exams. Hopefully, we'll see. I will rectify that as I go, because that's what's going to happen in the real thing, not just reeling off these perfect solutions. So it's probably going to be a big one. I'll stick chapters down at the bottom of the video so you can just jump to specific questions. But I think we just got to crack on, haven't we? So let's jump in. So we're starting with statistics. And question 1 says, Helen believes that the random variable C, representing cloud cover from the... they're jumping straight in with a large data set, right. From the large data set can be modelled by a discrete uniform distribution. Write down the probability distribution for C. Okay, right. There's not really any special tip I can give you here, apart from you just need to know the large data set. If you don't, you're going to have trouble with this question. Unless maybe your mum's a meteorologist, then you might get away with it. But I can't give you any secrets here, apart from just revise the large data set. If you do revise the large data set, you will realise that cloud cover is measured in octas, right? What is an octa? So imagine you kind of split the sky up, right, into 8 chunks. Let's do it in a circle, why not? Split it up into 8 chunks. Basically, an octa is just representing kind of how many of those chunks are filled with clouds. So if we imagine, right, if it's just in white, there's no cloud. So imagine that there was none of these chunks were filled up. This would just be a completely clear, nice sunny day. And then if one of them was filled up with, clouds, that would essentially correspond to what, like 1/8 of the sky being covered in clouds. And that would be kind of 1 octa. So, 2, I could have 2 octas, and then that would be, okay, about 2/8. So 1/4 of the sky is filled up, essentially. Okay, so we want a probability distribution. So when we think of that, what are we looking for? Well, a probability distribution is basically saying, right, here are the different values this random variable can be, and then these are the probabilities of each one of those values. So for C, I would write this. I would write, okay, different C values. And then the probability that big C, my random variable here, is equal to that little C value. These should technically be uppercase and lowercase, quite hard with C's because they look really same. But here we go. So essentially what we're going to need to do is we're going to need to write different possible values here and their corresponding probabilities. So look at this little pizza I got here. Well, we could have, 1 octa, we could have 2 octas, 3, 4, 5, all the way, we could have 8 octas. So there are 8 possible values, right? Well, not really, because we can technically have 0 octas as well. Like if I have a completely sunny day, no clouds anywhere, there's none of the sky is filled up. So none of this, pizza is filled in. So I can also have 0. So I can have 0 all the way up to 8, can't I? So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So it's now a case of working out what the probabilities of each one of these are. So what does a uniform distribution mean? That's what Helen thinks it is. Helen thinks it's uniform. Uniform means the same. It means basically every probability here is exactly the same. The probability of having 0 octas is exactly the same as 1, same as 2, all of them. In other words, these 9 chunks I have here are going to be split perfectly. So obviously the probability of all of it together is going to be 1. So the probability of 1 is just going to be 1/9. So every single one is going to be 1/9 here. And that is it. So, I mean, you can start thinking how likely that would really be, but we might get onto that later. They like to get us to kind of comment on things. Maybe always be thinking at the start of the question, well, does that really make sense? Well, they all have the same probability. But I reckon that's enough. I mean, it's only a couple marks here. So let's say you just didn't have a clue about the large data set. You're only losing a couple marks. Now, part B, using this model, find the probability that cloud cover is less than 50%. Okay, so this isn't going to be that bad at this point. So let's think to my sky again. 50% would be represented by half the sky filled up, right? So I want less than 50%. So I can't have exactly 50%. I want this much or less. So, well, what's that going to correspond to? If I have 2 octas, that would be less than 50%. If I only had 1, it would be less. If I had 0, it would be less. And if I had 3, it would be less. So this is basically going to correspond to the probability that C is less than or equal to 3. But now we have our distribution, this is a lot easier to do because we know all of these probabilities. It's going to be this one, this one, this one, and this one. So that's just going to be 4 lots of this 1/9, isn't it? Which is going to be 4/9. Sweet. Once we've got distributions, things get a bit easier. Okay, I think they want us to start talking now. So Helen used all the data from the large data set for Hern in 2015 and found that the proportion of days with cloud cover less than 50% was 0.315. Comment on the suitability of Helen's model in light of this information. So what they tend to do is they say, okay, given this model, work out a probability. So that's what I did in part B. And then later on, they'll say, well, actually, you know, the probability was this. So then it's usually a case of comparing these probabilities and saying, right, well, does the kind of model that you gave me, does that claim kind of work out with the other probability that we actually got in real life? And let's have a look. So 4/9, what's that? It's 0.4 occurring, right? So, you know, 0.444, etc. And then the value that, you know, the real value is 0.315. So they're a bit different, aren't they? You know, if the real value was like 0.415, I'd probably say, well, I reckon that's close enough to kind of be acceptable. 0.315, we're getting quite a lot of difference here, aren't we? You know, compare like kind of 44% to 31%. It's a bit of a big difference. So I would say here that I think 4/9 is just a bit too much bigger than 0.315. So I would say I don't think Helen's model is that suitable in this case. You know, if Helen's model gave me a probability that was really close to the actual value, then I would, you know, I'd say, okay, well, that could give me reason to think it's suitable, but I think 4/9 is just a bit too far. So I would basically say, you know, the model suggests the probability is kind of much higher than it is, right? So not too suitable, I would say that. Not too suitable. Fantastic. We don't need to write an essay, but just let the examiner know what you're on about. Okay, suggest an appropriate refinement to Helen's model. This is kind of what I was alluding to. I knew that I had something like this. It's kind of what I was alluding to before. What does Helen think? Helen thinks that you are exactly equally likely to get none of the sky covered than all of the sky covered, to half of the sky covered, to 5/8 of the sky, exactly, all the same probabilities. But do you think that's really the case? Have you ever like lived in Manchester in the winter? Tell me you've got exactly the same probability of a completely clear day to a completely cloudy day. You have not, right? So here's the thing, it's going to vary. It's going to vary on location. It's going to vary on the time of the year. Are you telling me that this probability distribution is going to be exactly the same in the winter than the summer? It's not, is it? So look, here's what I would say. I would say, look, the cloud cover, there's no way it's uniform. I would say cloud cover, what's it going to depend on? It's going to depend on location, definitely, time of year. So it's just, I don't think you can have a uniform distribution here. So I would basically say the appropriate refinement would just be don't use a uniform distribution. Surely the distribution is going to change, you know. I'm going to have different probabilities of having a completely cloudy day to a completely sunny day. So yeah, I reckon that's enough for question 1, so we are getting there. Question 2. Tessa owns a small clothes shop in a seaside town. She records the weekly sales figures, W, and the average weekly temperature for 8 weeks during the summer. Okay, so it looks like it's going to be something where she wants to see if these two things relate to each other, right? The product moment correlation coefficient for these data is minus 0.915. Oh, they're jumping straight in with the hypothesis test on question 2. Right, so it says, stating your hypotheses clearly and using a 5% level of significance, test whether or not the correlation between sales figures and average weekly temperature is negative. Right, what's kicking off? A lot of words are getting thrown about. Okay, so the product's moment correlation coefficient is basically something that says, okay, how do these two variables relate to each other? So it can be between -1 and 1, right? So if it's 0, that basically suggests there is absolutely no correlation between these two things. If it's -1, that suggests, okay, this is just a perfect negative correlation. In other words, one of them goes up, the other one goes down. If it's 1, it's a perfect positive correlation. So one of them goes up, the other one goes up with it. And then, anything in between. So maybe 0.5 would correspond to positive, but, not that strong, and etc., etc. So what we have is we have minus 0.915, which, suggests that that's pretty negative, isn't it? It's kind of over here. Now, we want to do a hypothesis test here. So what we're testing on is this population kind of coefficient. We call that rho, another Greek letter for you. So what that's basically saying is, okay, we're doing this test on rho. So what we're going to do is we're going to get a critical region that basically says, right, if your value of rho is, less than or greater than this, then that gives you sufficient evidence to think, actually there is this correlation here. So how are we going to get this critical value, and then how are we going to compare it to what's going on here? Okay, well, what we're going to do is we're going to get the tables up. So, right, there's a lot of numbers going on here. Now, what do we do? Here is the one for product moment coefficient. A lot of words. What we need to do is we need to say, okay, we need to take our sample size and compare it to the significance level that they want in the question. So let's look at what we have. It says 8 weeks during the summer. So that means that our sample size is going to be 8. So we're looking over this row. And what significance level do we want? We want 5%. So this 0.05 corresponds to 5%. So the number I'm going to care about is going to be this one here, 0.6215. Okay, but we're doing a hypothesis test, so remember there's just a checklist of things we need to do. The first thing, state our hypotheses, right? So my H0, let's go down here, is what? My H0 is that, okay, there isn't a correlation between these two things, and that would correspond to this value of rho just being 0. So it's H0 saying, look, that's the kind of base, rho 0, there's no correlation. And then Tessa's like, well, actually, I think H1, alternative hypothesis, that it's actually going to be less than 0, that there is this negative correlation, that rho is less than 0. And then all of our work up here is going to kind of determine what we can conclude about that. Remember, 0.6215 was our number. So let's go back to here. This table is basically telling me, look, if you've got a sample size of 8 and you want 5% significance, if the value that you get, if you're testing for a negative correlation, so it's worth noting that this works on a positive and negative sense, so this would be here. If you're testing for this negative correlation with this sample size and this level of significance, if you get a value from your data, your sample, that is less than minus 0.6215, then you've got enough evidence. You are in the critical region here. The critical region is basically this here. And we definitely are in the critical region, aren't we? Because we're right down here on minus 0.15. So I would say the following. I would say minus 0.915 is less than minus 0.6215. So I'm basically in the critical region. Therefore, there is enough evidence to reject my H0 and accept my H1. In other words, there is enough evidence to say, you know what? There is a negative relationship between these two quantities. So I'll say, therefore, there is sufficient evidence. Now, a cheeky one here, you want to say at the 5% level, because there might not be sufficient evidence at the 1% level, at the 10% level. So you need to say at the 5% level to suggest, I'm just going to say to reject H0 here, essentially. And that is more than enough, I reckon. So yeah, it's in the critical region, there's sufficient evidence. So basically, I think that actually it gets hotter and I start making less money. Fantastic. Okay, so part B says suggest a possible reason for this correlation. We'll have a think about it, right? Imagine you live in a seaside town, right? Gorgeous day outside, gorgeous, 30 degrees out. Might not be gorgeous for you international students, but in England that is. What are you going to be doing? Do you want to go buy a new pair of jeans? Nah, you do not. You're going beach, right? You're going to the beach. So honestly, I'd just say that. I would say, look, if it's hot, I don't think I want to go clothes shopping, right? So I'd say, on a hot day, people would be more likely you know, to go to the beach, to go out, than to, you know, go clothes shopping, I'd say. Done. That, you know, these ones, they really are just kind of common sense in these statistics questions. Right, let's have a look at part C. Tessa suggests that a linear regression model could be used to model these data. State giving a reason whether or not the correlation coefficient is consistent with Tessa's suggestion. Well, yeah, so essentially, correlation coefficient, if that's, you know, close to basically 1 or -1 that really suggests there is a correlation here, then that is consistent. Linear regression model is basically saying, right, okay, my data are pretty, you know, well correlated, so I'm going to basically come up with some kind of equation of a straight line here, you know, y equals mx plus c, right? To kind of more or less fit this, and then I can say, kind of make predictions. I can say, you know, when x is 10, what's y going to be? And you can go to your line of best fit kind of thing. So that's not really going to be appropriate if my value of r is 0, if they're just not correlated. You know, if it looked just like this, absolutely nothing going on here, how am I going to draw a straight line to fit that data? So in other words, if your value of r, you know, your sample correlation coefficient is near to 1 or -1, then it's going to be appropriate because I can do something more like this. So I would just say, look, my value that I got, what did I get? I got minus 0.915. That's very close to -1, isn't it? So value of r, which is kind of a sample coefficient, is close to -1, therefore that does seem appropriate. Therefore, you know, a linear regression model would be appropriate. I would say that. Fantastic. What does part D say? State, giving a reason, whether, oh no, that one, which variable would be the explanatory variable. Okay, so it basically means explanatory variable is like, right, this variable kind of changes and it affects the other variable. So think about this. The two variables are the temperature and the sales figures. Do you think that the amount of money that Tessa makes, you know, last week is going to affect the temperature of the town? I don't think Tessa's clothes shop has the ability to control the weather. However, I think the weather does have the ability to control her sales figures, as we said in part B, right? If the weather's higher, that can affect her sales figures because, you know, less people will go shopping. It's definitely not going to be the other way around. So the temperature is the thing that is explaining her sales figures, right? So it would definitely be the T here, the temperature. Say giving a reason. So yeah, so temperature, because that, you know, has the ability to affect the sales figures and not the other way around. In other words, you know, so you're going to be getting sales figures as a function of temperature. Let's make that bigger so you can actually read it. Now, part E. Tessa calculated. So she did all that, we don't have to do it, which is great. The linear regression equation as W equals 10,755 minus 171t. So in other words, that is saying, you know, my estimated, give me a temperature, I'm going to estimate how much money I'm going to make that week. Give an interpretation of the gradient of this regression equation. So what is the gradient? Let's write this out. W equals 10,755 minus 171t. So, you know, you can think kind of a y equals mx plus c, or in this case, it would kind of be y equals c plus mx, right? Because this is my explanatory variable here. The m, you know, this value of the gradient is going to be the minus 171. So it's basically saying, right, imagine the temperature's 0, I'd expect to make £10,755. If the temperature's 1, I'd expect to make £10,755 minus £171. Temperature goes up again, 10,755 minus 2 lots of £171. Temperature's 10 degrees, I'm take away 10 lots of £171. So if you think about it, the thing that this gradient is explaining is it's saying, right, well, each time I jump 1 degree in temperature, how does that affect my sales figures? So I would say the following. I would say, look, for every 1 degree jump in temperature, Tessa is expecting to lose, or to make, £171 less. So they really like you kind of translating, you know, these mathematical models into real-life interpretations. We've done a lot of writing in this question, but that is question 2 out of the way. Question 3, making light work of it. So, in an experiment, a group of children are repeatedly The children aren't thrown. The children each repeatedly throw a dart at a target. We ain't throwing kids anywhere. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. Peter? Let's go Peter, right? Models h as a binomial distribution, with n equals 10 and p being 0.1. State 2 assumptions Peter needs to make to use her model. So this is actually just asking us about the binomial model, right? So it's basically saying what assumptions do we need in a standard binomial distribution, not really anything to do with Peter. So one of the classics is independence. In other words, trials are independent. So in our context, that is going to mean whatever happens on my first throw does not affect what happens on my second throw, or my 8th, or my 10th. So throws are independent. And then another classic is basically the probability is constant. And that is reflected in this model because it says P is 0.1. P is 0.1 for the first, for the second, for the 8th, for the 9th, for the 10th, for all of them. So in the context of our model, that would mean that I have a constant probability of hitting the target on each throw. So let's go for that. Constant probability of hitting the target on each throw. Just 2 classic binomial assumptions that you really need to know. They're always going to ask them. Okay, so using Peter's model, find the probability that h is greater than or equal to 4. Now, my calculator gives me less than or equal to probabilities in the binomial. Doesn't give me greater than or equal to. So I think we need to be a bit clever here. So what are the different values h can be? Well, it's counting my hits, isn't it? So I could get no hits. I could get 1 hit. Could get 2 hits, 3 hits, 4, could get 5, 6, 7, 8, could get 9. I could get all 10 of them. Couldn't get 11 though, could I? Couldn't get anything more than that because I've only thrown it 10 times. And equally, I couldn't get -1, could I? So really, this is my list. There's no more possibilities, is there? I'm either going to get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 hits out of my 10 throws. So what that means is that, the probability of all of these added together is going to be 1, isn't it? Because that's everything. It's all the possibilities. I want this, don't I? I want the probability that it's greater than or equal to 4. So it's any of these. So what I could do is I could say, well, you know what? Isn't that just the same as everything, which is this kind of long line, which is 1, and then minus everything I don't want? So if I have this whole line, and then I take away what I don't want, what am I going to be left with? Well, I'm going to be left with this, the things that I do want. So what's this thing here? Well, this is going to be the probability that h is less than or equal to 3, isn't it? Why is that useful? Because that, my calculator can tell me it. So get it out, and we're going to press menu. We're going to press 7 for distributions. Now, I can see a binomial here, but that's not what I want. So binomial PD stands for probability distribution. Now, if it was like h equals 3, then we would use the probability distribution. However, it's less than or equal to. So what we're going to do is we're going to press down on our calculator, and then we're going to go to binomial CD. That means cumulative distribution. Because these probabilities are accumulating, it's, probability of 0 plus probability of 1 plus they're accumulating, it's cumulative. I'm going to press variable, which is just going to let me put in the relevant numbers and get my answer out of it. So x is the number that I'm interested in this case, which is the 3. N and P are just going to be the parameters of my distribution. So N is going to be 10 in this case, and P is 0.1. Straight in, and I get this. I get 0.987248. Just go a bit more accuracy than you're going to eventually round it to in your answer. So we now just want to work this out. So we need to get back into normal mode. So press menu 1, now we're in normal maths, and just stick it in. So it's going to be 1 minus 0.987248. And then let's round it to 3 significant figures. So I'm going to get 0.0128, and that is going to be to 3 significant figures. Sweet. Let's carry on. So part C says, right, for each child, the random variable f represents the number of the throw on which the dart first hits the target. Okay, so it's saying, when do you get your first hit? Do you get it on your first throw, on your second throw, on your third throw, etc.? Using Petter's assumption about this experiment, Probably butchering that name, sorry Petter. Find the probability that that f is equal to 5. What is the probability that f equals 5 in words? Well, it's the probability that the first time I get a hit is on my 5th throw. So what needs to happen for that to happen? Well, on my first throw, I need to get a miss, don't I? And then on my second throw, I need to get a miss. Third throw, I need to get a miss. Fourth throw, I need to get a miss. Getting a fuming at this point, but then finally on my 5th throw, I get a hit, don't I? So what's the probability of getting a miss? Well, if the probability of a hit, according to Petter, is 0.1, the probability of a hit is going to be 0.9, of a miss is going to be 0.9. So it's going to be 0.9, and then we need this to happen, and this to happen, and this to happen. So I'm going to be using the AND rule and multiplying these probabilities. So basically it's going to be 0.9 times the miss, times another miss, times another miss, and then finally times my hit, which is 0.1. So this here is 0.9 to the 4 times by 0.1, which straight to the calculator is going to get me 0.065. So I actually get it. This is it here, but I gave my other answer to 3 sig figs, so I'm going to do the same for this one. So I'm going to do that, and again, that's 3 sig figs. Let's be consistent. Okay, I think that's part C. Sweet. So let's have a look at this one. It says Thomas assumes that... I think the window's getting cleaned. Right, we're carrying on. Right. Thomas assumes that in this experiment, no child will need more than 10 throws for the dart to hit the target for the first time. He models the probability that that f equals n as. Probability that f equals n is 0.01 plus n minus 1 times alpha, where alpha is a constant. Find the value of alpha. Okay, what's going on here? So this is a new model, so we'll forget about the binomial now. This is what Thomas thinks is kicking off. What we could do here to get a bit of an idea is kind of write out this as a probability distribution, just like we did in question 1, where we said, well, what are the different values this thing can be, and what are those probabilities? So we could go different n values, and then the probability that f equals that n value. What's it going to equal? Well, n could be 1. I could get my first hit on my first throw. Could be 2. Could be 3. And then it could be anything. And then what does it end on? Let's look at what Thomas thinks. He thinks that in this experiment, no child will need more than 10 throws. So what he's saying that by 10 throws, everyone's got their first hit. In other words, that f can never be 11, can it? Because it's saying no, like they will have had the first hit in the first 10. So the last number that this can be is 10 here, which is good, because then we can say, okay, well then this is a finite list, and then we can use something cheeky. We can say, well, all of these are definitely going to add to 1, aren't they, if this is a finite list. So let's work out what these are going to be. If I sub n equals 1 into this formula, it's going to be 0.01, and then plus, well, n minus 1 times alpha, but if n is 1, then it's going to be 1 minus 1, which is 0, so that's actually it. And then what's going to happen is I'm just adding more alphas. For 2, I'm going to get 2 minus 1 lots of alpha, so 1 lot of alpha. So for 2, it's going to be 0.01 plus alpha. For 3, and then it's going to be, 3 minus 1 lots of alpha, so 2 lots of alpha. So we can kind of see a pattern. We're just adding alphas each time, aren't we? So all the way up to 10, which is going to be what? 0.01 plus, and then n minus 1, 9 lots of alpha. So this is nice, because what I can do is I can add all of these together and say that they must equal 1, because this is a finite list in all the possibilities. So that tells me that 0.01 plus 0.01 plus alpha plus 0.01 plus 2 alpha, etc., all the way up to 0.01 plus 9 alpha is going to be equal to 1. Okay, let's clean this up. There's kind of 2 bits of this. There's the 0.01s and the alphas. 0.01s are easy because they don't change. I'm going to have 10 of them, aren't I? So I've got 10 lots of 0.01 plus, and then what have I got? I've got alpha plus 2 alpha plus 3 alpha all the way up to plus 9 alpha, right? And that's going to equal 1. Well, first thing is, this is just going to be 0.01, right? 0.1. Did I say that? I can't remember. Let's take an alpha out of this. So I get alpha and then 1 plus 2 plus 3, all the way up to 9, right? Now, okay, it's worth mentioning that you can just put this into your calculator. Like, the numbers aren't massive, you know. If I just do 1 plus 2 plus 3 plus all the way up to 9 in my calculator, that's fine. For all you nerds out there, for which I am probably one of them, there is a formula that tells me how to sum n numbers, and it is the following. So let's just keep this here, and then keep the alpha here. It's going to be n times n plus 1 over 2. So my n in this case is 9, right? I'm summing the first 9 numbers. So it's going to be 9 times 9 plus 1 over 2. If you're thinking, what's he on about? Don't worry. Like, completely forget what I just said and just put that into your calculator. No worries. This is for the nerds. So equals 1. Looks a bit mad, but this is just an equation that has alpha in it. So I think I can solve this. So the first thing I'm going to do is I'm going to take this 0.1 over to this side. So I know I'm going to get a 0.9 here. So what have I got here? I've got alpha, and then 9 plus 1 is 10. 9 times 10 is 90. 90 divided by 2 is 45. So I actually have 45 lots of alpha equaling 0.9. So alpha is going to be 0.9 over 45, which seems to be 0.02, which makes sense. It should be a small probability, right? It's a number because we're in probabilities. Everything's less than 1 here. So I think that's it. I think that's the hardest part of this question. I wouldn't expect many people to get that, so don't worry if you're a bit like, what's kicking off here? Using Thomas's model, find the probability that f equals 5. At this point, it's easy. Now that we have alpha, shouldn't be a problem because just put it straight into that formula, right? So we know the probability f is n, so we just swap n for 5 in that formula. So it's just going to be what? 0.01 plus 5 minus 1, and then times alpha, which we now know. If you didn't get alpha in part D, sorry, but you kind of get part E, just write alpha here and just work out the answer in terms of alpha. You might get a mark because it's saying, well, you know, yeah, you didn't get the marks for part D, but you at least understood part E, you know, as a kind of independent part. So, you know, I would definitely do that. If you ever see something where it's like, oh, if only I knew that part, I'd be able to do this one. Just do it in terms of algebra. Why not? Just put this into your calculator. So 0.01 plus bracket 5 minus 1 times by 0.02 is going to get me 9 over 100, which is 0.09. Okay, last one. Explain how Petter's and Thomas's models differ in describing the probability that a dart hits the target in this experiment. So it's kind of relating to part A, isn't it? Remember what we said in part A? Petter thinks, because it's binomial, that the probability is the same. You know, that all of the time, the probability that anyone is getting this target is 0.1. So Petter thinks that it's constant, right? Petter thinks the probability is constant. You know, always 0.1. Thomas, however, what does Thomas think? Well, look at this kind of thing with the alpha. Thomas thinks that, you know, the probability of me getting my first hit is 0.01, I believe. And then the second, it's a bit higher. Third, it's a bit higher. Fourth, it's a bit higher. So Thomas actually thinks that as you start throwing, you're kind of getting into the swing of things, right? You're getting your practice in. The probability of you getting that hit is increasing, doesn't it? So Petter thinks it's constant. You're not getting any better. Thomas thinks that the probability increases. That the probability increases with each attempt. So probability of getting a hit increases with each attempt. Tough question there. A few pretty dodgy bits, and you've got to be really careful with kind of, you know, which assumptions you're using when you're doing your calculations. So yeah, if you find that one tough, I would say that's pretty normal. Question 4 looks absolutely massive. Right, here we go. Charlie is studying the time it takes members of his company to travel to the office. He stands by the door to the office from 8:40 to 8:50 one morning and asks workers as they arrive how long the journey was. Is it the sampling method Charlie used? Okay, so all he's really doing is he's just standing there and then he's asking anyone who comes in. He doesn't have any other system about it. He's not saying, okay, I'm going to ask someone every X minutes, or I'm going to make sure I ask this many males, this many females. So just saying, right, how long does it take you? Kind of thing. So this is just what we call opportunity sampling. He's just taking the opportunity, someone's coming in, taking the opportunity to ask him. Could also be called convenience sampling. It's just pretty convenient, isn't it? They're there, ask them. So opportunity or convenience sampling is basically the same thing. Looks like I've forgotten how to spell convenience. Right. Okay, so yeah, that's it. Don't even have to explain it, which is nice. Part B says state and briefly describe an alternative method of non-random sampling Charlie could have used to obtain a sample of 40 workers. So what they tend to be looking for in questions like this is like quota sampling. So, make sure that your sample hits a certain quota. So, I mean, one kind of variable you could do it on is like males and females. So I could say, okay, I want to, ask people till I hit this certain quota of X males and X females. Here it says sample of 40 workers. So, I mean, it would make sense to kind of balance the males and females, right? So you could basically just say, look, you can basically, decide on this quota. So you could say, 20 males, 20 females, and basically just make sure you get that in your sample. So make sure to get a sample matching a quota of 20 males and 20 females. I should make sure that I actually write the name of the sampling method as well to get the marks. I reckon that'll do the job there. Okay, so few easy marks. Part C. Taruni decided to ask every member of the company the time in minutes it takes them to travel to the office. State the data selection process Taruni used. Okay, well, Taruni's not actually getting a sample because they're asking everyone. So this is actually what we call a census, right? It's basically you ask absolutely everyone in the whole population. The whole population of the office is getting a census. And great, we don't have to explain it. So this is good, We're not having to do many words here. Okay, so Taruni's results are summarized by the box plot on summary statistics below. Right, write down the interquartile range for these data. Right, let's get this box plot up. Interquartile range is basically just the upper quartile. So this thing here minus the lower quartile. So how much are these squares worth? It looks like they're each worth 2 because there's 5 in this jump of 10. So just work it out. So this thing here is going to be 26. This thing here is going to be what? 50 and then 1, 2, 3, 4. So 58. So it's genuinely just the interquartile range is just going to be 58 minus 26, which, if we can remember how to do mental maths, I believe is going to be what? 32. And that'll do the job there. Right, okay. The nice little questions, which is good. Calculate the mean and standard deviation for these data. All right. Mean is where you just add them all up and divide them by the amount there are. And because we've been given these summary statistics, it's quite nice because our mean x bar is just going to be this sum of x, which is, all of them added together. So the 4, 1, 3, 3 divided by how many there are, which in this case is 95. So that straight to your calculator. It's going to get me what? It's going to get me 43. Let's go 3 sig fig here. So that's going to be 43.5 to my 3 sig fig. Cool. Standard deviation is a bit more of a mad one, but essentially it's the following. So it's the square root of, are you ready for this one? It's going to be the sum of the x squareds all over n and then minus the mean squared. And we've already worked that out, which is nice, so we can just do that. So luckily, it's now just a case of subbing numbers in. So it's going to be the square root of, so we have this sum of x squared. It's 202,294. We know that n is 95, and then minus this value here squared. Now, I just want to make sure I minimize any rounding errors, right? Now, I rounded this here. So I don't know if it's going to make a difference, but I don't want to risk me putting in the rounded value here and then not getting the right answer come out for the standard deviation. So in my ants on my calculator, I've still got the answer that's not rounded. And it turns out it's a fraction. So if you were to use this, if you were to just keep it there and then use that value and then I can round at the end. That just really eliminates that risk, basically. So I can put all of this into my calculator here. So it's going to be a bit mad, but I'm going to get 202,294 all over 95, and then minus. Now this is actually still saved as ants in my calculator. So minus ants squared. And that, to 3 sig fig, is going to be 15.4. And I know I've not got any rounding errors now. Fantastic. Part F, okay. Big question, but at least the parts go quickly. State, giving a reason whether you would recommend using the mean and standard deviation or the median and interquartile range to describe these data. So it's always that kind of trade-off between, okay, do I use the mean? You know, what are the advantages and disadvantages versus kind of the median? Now, in this case, let's have a look at this box plot. Outliers are generally a bit of like a, you know, we purposely exclude them. Like here we excluded them, didn't we? We said they're just too mad. They're going to skew the data too much. So we excluded them. So here's the thing. Box plot, when we were working out our quartiles, our medians, all of that stuff, we just ignored these outliers, which is nice. However, when I work out the mean and standard deviation, so these summary statistics, these outliers are included, aren't they? Because the mean is all of the values added together. So these are going to be included. They're going to skew it quite a lot towards this way. Same with the standard deviation, you know, sum of x squared, and it's a function of the mean too. So here's the thing, the median and interquartile range, they don't care about these outliers. They are not susceptible to them. But the mean and the standard deviation are. So I would say in this case, I'd probably rather use the median, right? Because I've got these outliers that are crazy. I mean, the median's around 40, and look at this. This is like 2 hours, 120 minutes. It's a lot. It changes the data a lot. So I would just say, in this case, what do they exactly want? Giving a reason whether you would recommend, yeah. So I would say median and interquartile range, because they are not affected by the 2 outliers. Because you're saying the 2 outliers to really show, okay, I know this general thing about the median, but then I'm applying it to this question. And I reckon that's enough for 2 marks right there. Whereas obviously the mean and the standard deviation are affected. Okay, cool. Last part, finally, right, Rana and David. Both work for the company and have both moved house since Taruni collected her data. Rana's journey, Rana, I'm sorry, not been good on the names today. Her journey to work has changed from 75 minutes to 35 minutes, and David's journey to work has changed from 60 minutes to 33 minutes. Taruni drew her box plot again and only had to change 2 values. Explain which 2 values Taruni must have changed and whether each of these values has increased or decreased. A lot of words. Let's go back to this box plot so we can see, okay, like what's happened. Let's look at Rana. Okay, so it's changed from 75. So it was like here, right? And it's now gone to 35. So it's gone from here kind of to like there, right? David has gone from 60, so here, to 33. So kind of around here. Okay, so they've both kind of gone down. So that's instantly leading me to whatever values changed, they must have decreased, right? So let's have a think. These values haven't changed. They're still outliers. They're still right on the end, aren't they? Have these values changed? Well, they've not, have they? Because, you know, these are the lowest and biggest values outside of the outliers. Neither of those was these 2, were they? These 2 were already inside, so there are still values here and here that have not changed. So they're definitely not changing. Has this changed? Well, this is to do with kind of, you know, the 25% of people that are in here. None of those have been affected. No one has left that group, and no one has entered that group. So this is not changing at all, has it? So that only leaves us with these 2. They're going to change, aren't they? Because look, people have left this upper quartile now, so this is definitely going to change. This is going to be in a different place. And then the median is definitely going to change because look, I had 2 values that were greater than the median and have now been shifted over to the other side of the median. So the median and the upper quartile have changed, and will they have gone down or up? Well, look, both of these values are going down here, so they're both going to decrease. So it's basically going to be the median and the upper quartile. And if I can learn how to type, they will both decrease. Okay, absolutely mega looking question, but luckily wasn't as long as I initially anticipated. Okay, I believe I'll only have one more stats question to go. Good news, this is the last question of stats. Right, let's go through it. So it says the lifetime L hours of a battery has a normal distribution with mean 18 and standard deviation 4. Before we even carry on, normal distribution, let's just get it down so we really know what we're working with. L is distributed normally with a mean of 18. Now the second parameter isn't just 4, it's 4 squared, and that's because the second parameter is sigma squared in a normal. Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. And the probability that a randomly selected battery will last for longer than 16 hours. Okay, so we're just talking about one battery here, so we don't need to worry about this whole Alice's calculator requiring 4. This is just a standard normal probability, which we can use our calculator for. So what we're going to do is we're going to go to menu 7 again. We're going to go normal CD. Then you see we put lower and upper in. So essentially, right, a normal distribution, the classic bell curve. That was awful. I'm gonna do it again for you here. Never been the best at doing this. There we go. So, 16's here, and I basically want the probability that it's greater than 16, so anything here. So essentially, this is an area, and you want to bound it by lower and upper limits. We don't technically have an upper limit here, do we? Because we just want it to go over to infinity. We just want anything greater than 16. So what we can do is we can just say, look, because these probabilities at the end are so low, if we just put in a really big number, we know that we're pretty much going to be there because we're not really missing out on much probability over here. So, some people say things like, oh, put this many standard deviations above the mean or whatever. I just get my finger, put it on the 9 and just go like that because that's obviously just a massive number. And so that's all we really need to do here. It's just definitely going to encapsulate it. The lower limit is going to be the 16 here. And then for the sigma and the mu, we just put in our parameters. So sigma is going to be 4 and mu is going to be 18. Straight away, put that straight into my calculator. And that's going to get me 0.69146246117, all of that stuff. Let's go to 3 significant figures. It's going to be 0.691. Fantastic, that's it. Easy as, quick 1 mark. At the start of her exams, Alice put 4 new batteries in her calculator. She's used the calculator for 16 hours, but has another 4 hours of exams to sit. Oh, she's playing it. She's playing it dangerous here, Alice. Right, find the probability that a calculator will not stop working for the remaining exams. Right then. Okay, so let's have a think. We need an extra 4 hours of battery life. For 4 batteries, actually, but let's think about 1 battery and then we'll work out the kind of 4 thing later. So for 1 battery, what do we need for this 1 battery to carry on surviving? Think about it. It's already 16 hours old, right? So what do we need its age to at least be for it to last these extra 4 hours? It's going to have to live till it's at least 20 hours old, isn't it? So we kind of know we're going to need some at least 20 in there. Now, it's not just this probability though, because we actually already know something. We already know that it's lasted at least 16 hours because, she's used it for 16 hours. It's still going strong. So we don't want the probability L is greater than 20. We want the probability L is greater than 20 given that it is already greater than 16. Okay, now, this is a conditional kind of probability. I'll give you a quick kind of recap, but essentially the probability of A given B is going to be the probability of A and B over the probability of B. This, if you ever hear the words conditional probability, you think this. This is the only thing I care about. Now, put it straight in. So this is going to be the probability that L is greater than 20 and L is greater than 16 divided by the probability that L is greater than 16. Just think of this top probability. Think about it. Probability L is greater than 20 and greater than 16. But surely if it's greater than 20, then it is greater than 16. Right, think of a number that's greater than 20. Is it greater than 16? Yes, it is. So what this actually tells me is that I don't need to even care about this probability that L is greater than 16 here, because I know that it's completely encapsulated in the probability of L being greater than 20. So all I actually have here is the probability L is greater than 20 over the probability L is greater than 16. That's it. L is 20. Now, in my calculator, I've actually already got a lot of stuff from last time, from part A, right? So I've got my upper as just some madly high number. I've got my sigma and my mu. All I need to do here is change the lower. The lower is now going to be what? 20. So just put that in. And I've got the following 0.308537, whatever. Just go accurate. Why not? And now we've already worked out this up here, haven't we? So I'm not going to use the 0.691, as I was saying in the other question, just to eliminate any risk of rounding errors. When I'm using it in a calculation, I would much rather use the unrounded version. So, all of this, basically, just to really make sure I'm not introducing rounding errors, right? Go back to the normal mode on your calculator, menu 1, and then just work this out. So 0.308537 over 0.69146244617, more than enough accuracy there. And to 3 significant figures. Well, let's just write it all out for now. 2100506. The reason I'm not rounding it quite yet is because I don't think this is our final answer. Think about it. This is for 1 battery, but she needs all 4 to work. So really she needs battery 1 and battery 2 and battery 3 and battery 4. And when we want and probabilities, what do? We multiply them. In other words, the probability that, the calculator survives is going to equal this thing here, which I'm going to copy and paste because I'm lazy, to the power of 4, because it has to happen 4 times. Now, luckily, I've got this stored in my answer on my calculator, so I don't need to type it in again. I just press ans to the power of 4 to get me 0.039642116 ... which to 3 significant figures is going to be 0.0396. Fantastic. So it's, it's your normal stuff, but then with a bit of kind of extra logic in there too. Okay, so that is part B. Let's have a look at C. Alice only has 2 new batteries, so after the first 16 hours of her exams, although a calculator is still working, so we know that the L is greater than 16 for all of these, she randomly selects 2 of the batteries from her calculator and replaces these with the 2 new batteries. Show that the probability that her calculator will not stop working for the remainder of her exams is 0.199. Okay. So they've given us the answer, so we know that we have something to check over, right? So what needs to happen here? We've got 4 batteries, haven't we? We have got 2 new batteries and 2 old batteries. By old, I mean, obviously, they've been going for these 16 hours. So for all of these to survive, what needs to happen? Well, the new ones, they are 0 hours old, aren't they? So all they really need to do is survive 4 hours. So we need at least L to be greater than 4 on these. And then for these older ones, what do we need for them to survive? Well, it's kind of this probability we did up here, isn't it? It's this greater than 20, given that it's already greater than 16. So that's basically what we do. So let's go L is greater than 20, given that L is greater than 16, and then the same for that one too. You know what I mean? So again, it's and rule, isn't it? I need this one to survive, and this one, and this one, and this one. So we're multiplying the probabilities. So again, now the probability of survival, right, is going to be what? Well, it's going to be the probability that L is greater than 4, and then 2 of them, so I'm squaring it. I'm going to give more brackets here just to really show that I'm squaring this probability. And then multiplied by this thing here, so the probability that L is greater than 20, given that it's already greater than 16, and then 2 of them again. Now, this one here, we can work out with our calculator. So I'm going to go back to menu 7, normal CD. Lower now is going to be 4. Again, upper, just something mad, just smash the 9 button a load of times. Sigma, we know, is going to be 4, and my mu is 18. And that is going to get me, obviously, a really high number, because think about it. The mean is 18 hours. The pack says, right, this is going to last for 18 hours. The probability it's going to last more than 4 hours is obviously going to be very high. You're not going to expect it to die after 4 hours if it says it lasts for 18, right? So that makes sense that this number is just ridiculously close to 1. It's 0.99976737709. That makes sense. And I have to square that. Multiplied. Now, wait a minute. Haven't we already worked out this probability? Isn't it this number here without the power of 4? So this number here. So this is then going to be 0.44621. You don't need to do this many decimal places. You really don't. I just want to kind of hammer in the fact that you generally want to be working with more decimal places than you're going to be rounding to for your final answer. And I'm going to need to square this because I've got a squared here. So at this point, I'm going straight to the calculator. Now, I've already got this first one kind of saved, but I do need to go back to the normal mode. So I'm going to do 0.99976737709 squared multiplied by 0.44621000506 all squared. And lo and behold, to 3 significant figures, I get 0.199. Fantastic. So you can kind of see that her tactic has worked, right? In the last case, her probability of survival was only 0.0396, whereas now she's replaced 2 of the batteries, her probability of survival is 0.199, so just less than 20%. I still wouldn't bank on those odds, so I would definitely replace, those batteries before your final exams, but at least her probability has increased. Okay, so part B, what have we got? After her exams, Alice believed that the lifetime of the batteries was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2 hours. So Alice is obviously very bored. Stating your hypotheses clearly and using a 5% level of significance, test Alice's belief. Right, we've got another hypothesis test, this time in terms of a normal. So at a, overview, high level, what are we saying? We're saying, right, assuming our old mean was true, my kind of H0, which we'll get to in a second, essentially what was believed to be true kind of with this 18. We're basically saying, right, we want this 5% level of significance here. So this is going to be some number here corresponding to 5% level of significance. So it's basically saying, if kind of my result here from my sample is going to be greater than this, that might lead me to believe to say, actually, this won't be true, because if I got this result and this H0 was still true, the probability of me getting this result would have been very low, would have been less than 5%. However, if my result kind of lies in here, then it's saying, no, this is still within the realms of possibility with this old mean of 18. That's a high level view, but let's kind of actually set this hypothesis test up a bit better. So basically, what is assumed to be true is that mu is 18. Now, what does she think? Well, Alice believes that it's actually greater than that. So Alice believes that mu is greater than 18. Now, we need to be super careful here, and it's to do with the fact that she took a random sample of 20 of these. So we're not quite working with the exact normal distribution we had before, because the sample mean of a normal distribution is normal with the same mean. However, so it's going to be a mu here, because we're now not saying it's 18, we're saying, well, it could be, it might be greater. And then instead of just having this 4 squared here, we actually have 4 squared divided by 20. In other words, the bigger the sample I get, the lower the variance, which kind of makes sense, right? You do think you have a bigger sample, you expect it to jump about a lot less. So you could write it like this, or you could also write it as 4 divided by the square root of 20 all squared. Now that's kind of important, because now that's kind of my new sigma, isn't it? Because I'm going to end up putting that into my calculator. So what are we saying here? We're saying, okay, this is now kind of my X bar distribution. She got a result using this sample mean that was, where was it? 19.2. Okay, so she got a result of 19.2. And essentially, the question now is, well, where would that significant region lie here? If, for example, the significant region, the critical region, was here that corresponds to 5%, then I would be within that and I can reject. If not, then I can't reject. So how am I going to get that? And I believe I can use the trusty old calculator. So essentially, here's what we're going to do. We're going to say, we're going to find the probability. If this was the case, if it was 18, we're going to find the probability that, the sample mean is greater than this 19.2 value. So we're going to find out where it is. So we're going to find this out, and we can use the calculator for that because we now know everything in my distribution. So I'm going to go back to the normal. So menu 7, normal CD. Lower is now going to be 19.2 because I'm trying to work out this probability, the area corresponding to that. The upper, again, massive number, why not? Sigma now is not going to be 4, it's going to be 4 over root 20. So just literally write 4 divided by the square root of 20 in this. And then the mu is the same at 18. Okay, if this was the case, if it was at 18, the probability of me getting this sample mean would be what? Would be 0.0898. In other words, around what? 8.9%. That would be the chance of me getting a sample mean greater than this. So what does that correspond to here? Well, that would mean that all of this area is 8.9%. But wait a minute. Wasn't the sample mean, wasn't the significance level, for the 5%? Yes. So basically my critical region would have actually been anything here that would correspond to the 5%. In other words, this result isn't significant enough because I'm not yet in that critical region. If it was up here, then I'd be in the critical region, but I'm not there yet. So in other words, this isn't actually that much of a freak result given that the mean is 18. It would happen 8.9% of the time. So basically, I would say this. I would say 8.9% is greater than the 5%. And then I would just give it a bit of the old words. They love that in stats. So, therefore, not enough evidence at the 5% level to suggest that the mean life of the batteries is greater than 18 hours. In other words, cannot reject H0. A lot going on there, but I believe we are done with the statistics section of the paper. We're into the good stuff. It's mechanics. So let's have a crack at this one. Just a one-parter. It says, time t seconds, where t is greater than or equal to 0, particle P moves in the xy plane in such a way that its velocity is given by this old chestnut. So what we got? We got t to the minus a half, lots of I, minus 40, lots of j. So I and j are basically its horizontal and vertical position, or in this case, velocity. So it's basically t to the minus half in the I direction and minus 40 in the j direction. When t is 1, p is at the point A. When t is 4, p is at the point B. Find the exact distance AB. Okay, so obviously it's talking about kind of position, right? But we've got velocity. So what we actually need to do, there's a relationship between acceleration, velocity, and displacement, or kind of position. You can think of them kind of interchangeably in this sense. Basically, it's to do with differentiating and integrating. So basically, you would have, position or displacement, however you want to say it, velocity and acceleration. And then basically, if I differentiate this way, so if I differentiate R, I get V. If I differentiate V, I get A, which means if I integrate A, I get V. And if I integrate V, I get R. So that's what I'm going to need to do here. I want to know about the position here. So I'm going to integrate. So I'm going to say R is the integral, and then of all of this stuff. Minus half lots of I, minus 40 lots of j with respect to t. Okay, so what's going to happen here? I'm going to get, let's add 1 to the power and divide by the new power. So add 1 to the power, I'm going to get t to the half. And then dividing by a half is the same as multiplying by 2. So I'm going to get 2t to the half. And now, let's talk about constants for a second. Obviously, this is an integral. Now, usually you would kind of have like a constant. But this is a vector. So it's almost like you could have a constant for the I bit and a constant for the j bit. So there's a couple of ways you could do this. You could say maybe ci here, and then that's kind of the lots of I. And then I would integrate this. So I would say, okay, well, 4t is going to go to 2t squared. Add 1 to the power of that with a new power. So it's going to be minus 2t squared. And then I could say, and then plus some other kind of cj, and then lots of j, right? So I'd rather do it like that. Alternatively, I could just have the constant as a vector. So I need to make sure that there's kind of a constant in both the i's and the j's here, if that makes sense. So let's leave it like that for now. So these are just the normal bits of integrals, and then I've just stuck an extra little constant for each bit there. So what do we want? It says when t is 1, p is at the point A. When t is 4, p is at the point B. Find the distance between A and B. So this is a really important point relating to the constants. Now, the position is really, the thing that changes is to do with the t's. And then obviously these constants are tagged onto the end. But what I want here is the difference between two different positions. So, essentially I'm going to be doing one of the positions take away another. The constants are going to cancel. Now, I'm going to show you that though, in case you're a bit confused by what I mean here. So I am going to keep the constants in here just so you really get it. So what I'm going to do is I'm going to find the point A and I'm going to find the point B. So I'm going to sub the t equals 1 into here to get A. So I'm going to say that basically A is what? Let's sub t equals 1 in. So 2 times 1 to the half is 2. And then let's keep the constant here. So I get 2 plus ci, lots of I. And then plus, subbing 1 here, I get minus 2. So minus 2 plus cj, lots of j. So that's the point A. I don't quite know it yet because I've got these constants, but don't worry about that yet. So let's go for B. B is going to be what? I'm going to sub in t equals 4. So 4 to the half is the square root of 4, which is 2. So 2 times 2 is 4. And then plus ci, lots of I. And then 4 squared is 16, times that by minus 2 to get minus 32. So that's going to be minus 32, 3t, 32, plus cj, lots of j. So you might be thinking, well, what's kicking off here? I've got all these constants, I can't find anything out. I don't want to know exactly where A is. I don't want to know exactly where B is. All I care about is the distance between them, right? So what am I going to do? I'm just going to say, okay, well, if A is here and B is here, what is the difference between them? How do I get from A to B? So A to B kind of as a vector, what we're going to do, we're going to do B minus A, aren't we? Okay, so then, well, let's work that out. So in terms of the I's, what am I going to have? Let's just write it all down so you can see what's kicking off here. I'm going to have 4 plus ci, right? Minus the ones from A, so 2 plus ci. Lots of I. And then in terms of the J's, what am I going to have? I'm going to have minus 32 plus cj minus 2 plus cj. Lots of j. Well, can we see what's happening? What am I going to have here? I'm going to have 4 minus 2, so 2, and then ci minus ci. Ci's cancel, so we get 2i. What am I going to have here? I'm going to have minus 32 minus 2, so minus 32 plus 2, which is going to be minus 30. And then cj minus cj. Cj's cancel. So this is just going to be minus 30j. So this is the thing. We don't need the constants if the only thing I care about is the distance between them. Okay, so I've got AB, but we want this as a distance. So how do I get the distance if I have the vector? Well, 2i is basically 2 going that way, and then I've got 30 going down this way. So, it would kind of be represented like this. So the distance is just going to be that there. And we all know how to get this. We're going to use Pythagoras. So we're just going to say that the distance AB, which we can write as this, is going to be the square root. That was an absolutely dodgy line, but we've got a 2 squared plus 30 squared, right? Straight to your calculator. Looks like I'm still in the stats mode. Let's get rid of that. And then we get 2 squared plus 30 squared, all square rooted, to get me a pretty grim looking answer, but there's nothing wrong with it. 2 times the square root of 226. And again, it says exact, so I want to keep that as a cert, don't I? Because if I then, press the SD button, I'm going to get a decimal and I have to round it, so it won't be exact. That's question 1. Question 7, otherwise known as question 2 of mechanics. Looks like we've got a lot of text here, so let's give it a read. It says a wooden crate of mass 20 kilos is pulled in a straight line along a rough horizontal floor. Cool. Instead of just reading this whole thing, it's boring, I'm going to kind of talk about it as we go. So obviously rough horizontal floor, that means there's going to be friction. Cool. It's inclined, the handle is inclined at an angle of alpha to the floor, where tan alpha is 3/4. Again, I'm going to talk about this before we go on, so it's not just lost. Why don't they just tell us alpha? Why have they told us that tan alpha is 3/4? Why don't we just say, well, alpha is this? It's because they want you to realize something. Now, yes, we could just do the inverse tan of 3/4 to get a value for alpha. However, what's going to happen if I do that is that I'm going to get a rounding error because it's going to be some decimal. I'm going to have to round it to however many decimal places I want. Then when I use it later on, maybe as a cos alpha or sine alpha, I might then lose some of my accuracy and not get an exact answer. However, if I was to say, you know what, tan alpha is 3/4. If I was to draw a triangle, and I had value of alpha here, right angle triangle, and then, well, think about it, tan is opposite over adjacent, right? So let's give you a bit of SOHCAHTOA here. SOHCAHTOA. Now, that would mean that this would be 3, the opposite, and then the adjacent would be 4, because then tan alpha would be 3/4. But wait a minute, can't I use Pythagoras on this triangle to get this? To which the answer is yes, and by the way, it's 5. And then I can say, well, can't I just get sine and cos directly from this triangle without ever having to even get the value of alpha, right? Because SOHCAHTOA, I know that sine alpha is going to be what? Opposite over hypotenuse, so opposite, which is 3, over hypotenuse, which is 5. I also know that cos alpha is going to be what? It's going to be adjacent over hypotenuse, so adjacent 4 divided by 5. So look at this. We know that when we resolve forces and stuff like that, we use cos and sine of alpha. We never use alpha on its own. So look, I have no idea what alpha is, but I don't care. I've got these perfectly exact fractions that I'm just going to use in my calculations. So that's really going to help me here. So that's just a nice little thing I like to just get out of the way before I get into the nitty gritty. Perfect. Let's carry on reading. Tension in the handle is 40. We know that. The coefficient of friction between the crate and the floor is 0.14. Cool. The crate is modeled as a particle. That's the classic. And the handle is modeled as a light rod. That just basically means we can do all of this maths we're about to do. Using the model, find the acceleration of the crate. Okay, you know what I'm about to say. Get a diagram up. So let's get this up and let's just see what we have. We've got a reaction force that is always perpendicular to the plane, straight upwards in this case. So I'm going to get an R going up. We always have a weight going straight down, right? And the weight is going to be mass times acceleration. So that's going to be 20g. Mass times gravity, 20g. What else do we have? So obviously it's, it's going to be pulled along this way, isn't it? It's going this way. Friction. It's got friction, hasn't it? It's rough. It's got friction. Now friction is going to be opposing the motion. So there's going to be friction going this way. So I've got an F going this way. I think that's it. So essentially we kind of got a lot going on. There's 4 forces here. Let's have a look at what we need. We need the acceleration of the crate and just 6 marks straight in there. Okay, let me kind of have a talk about a bit of tactics here. You might not know exactly how to get the answer right here, and that would be absolutely fine. I don't know exactly how it's going to come out. But what I do know is the following. There are always the same equations that are going to apply to this situation, and there's going to be no difference. I know that in the vertical line here, it's not accelerating at all. So basically it's in equilibrium vertically. It's not going up or down. So in other words, I know that up equals down is going to apply. So before I even, I might not see exactly how this is going to lead me to an answer, but trust me, it's going to be relevant. So look, you have no idea how to do the rest, but you know that up equals down applies. Do your up equals down, right? Do your up equals down. You're going to get something. You'll either stop there and get some marks for it, or you'll be like, oh, no, wait, and then I can substitute that into that, etc. I also know that horizontally it is accelerating, isn't it? So F equals ma is going to apply. So I'm going to have the up equals down, and I'm going to have an F equals ma. So let's do the up equals down, first of all. So everything taking this thing up equals everything taking it down. Well, what do we have up? We have r. And then plus the component of this going upwards. The way that I like to do this is basically saying, look, it's going to be cos or sine. The kind of line that I want is this one here. So to get from my 40 to this line, I need to go away from my angle. This is the way I've always remembered it. Away is always going to be sine. And then if you go across the angle, it's going to be cos, but we'll get to that when we do the f equals ma. In other words, this thing here is basically just going to be 40 times sine of alpha. And that's going to equal everything taking it down, which is 20g. Now this is good because straight away the only unknown here is actually r, because I know what sine of alpha is. So I can rearrange this equation to get r, and I'm sure that it's going to be useful later on. So let's do that. So I'm going to get r equals 20g minus, and then 40 sine alpha. So 40 sine alpha is 3 over 5, isn't it? So r is going to be 20g minus, and then 40, let's try and work this out. So 40 divided by 10 is 4. So 40 divided by 5 is going to be 8. And then 8 times 3 is going to be 24. Now, I can work this out. I can put 9.8 in. Why don't I just keep it like this for now? And then later on, I can, get into the calculator and really get the values of stuff. So I've got my value of r. Now let's try my f equals ma. So f equals ma, the way that I like to do it, because I see students kind of they make mistakes on this quite a lot because it is quite difficult. One of the first things that people get confused about is this f means resultant force. So it's not actually a specific thing on the diagram. So what I like to do is say, okay, f, but then instantly I'm going to replace this with the following. It's accelerating towards the right. So in other words, this f is going to represent the resultant force to the right. In other words, everything taking it right minus everything taking it left. So I literally write the arrows, arrows help in equations, because then it says, okay, now I can look to my diagram. So that right take away left is going to equal ma. So let's look to my diagram. What's taking it right? Well, there's only one thing. It's going to be the horizontal component of that 40. Now remember what I said last time. If I'm going across the angle, it's cos. I want basically this arrow now, don't I? I want its horizontal component. To get from the 40 to the arrow I want, I need to go across the angle. So it's going to be cos. So in other words, this is going to be 40 cos alpha here. So I get 40 cos alpha, taking it to the right, minus what's taking it left, just the friction, and that's perfectly horizontal. So minus the friction is going to equal mass, which is what? 20 times A, which we don't know yet. That's going to be our unknown, right? 20 times A. Okay, let's have a see kind of what we have. Cos, we know what that is. So this is going to be 40 times by 4 over 5 minus f. What's f? Obviously, at the moment, it seems to be an unknown. However, we know that f is equal to mu r. Now, the technical equation is f is less than or equal to mu r, meaning that f max is equal to mu r. How do we know that the friction is at its maximum at the moment? Because it's moving. So we know that the friction is doing all it can. Because if it could do more, it wouldn't be moving, right? So friction is at its max. So basically, I know what mu is, don't I? Because they tell us in the question that it's 0.14. That's the coefficient of friction. So I can say 0.14 and then minus this value of r, which I worked out before for my up equals down, 20g minus 24. All of that is going to equal 20 lots of A. Now, I've got a lot of stuff here. You know what? I can't even be bothered trying to sort it out because I've not touched my calculator yet. If I just divide everything by 20, I'm literally going to get my answer for A. And that's going to be the only time I have to touch my calculator. So I'm going to say A equals, look at this. You can't copy and paste in real life, so sorry about that, but I'm going to cheat here. Boom, right? So A is going to equal all of that over 20. And now, straight into the calculator, minimized rounding errors. Let's have a look. So big fraction, 40 times by 4 over 5 minus 0.14 times by 20 times 9.8 minus 24 all over 20, which gets me 0.396 meters per second squared. I used g equals 9.8 there because I hadn't been told otherwise. Fantastic. Okay, let's have a look at part B. The crate is now pushed along the same floor using the handle. Cool. The handle is again inclined at the same angle alpha to the floor, and the thrust in the handle is 40 newtons as shown in the figure below. Explain briefly why the acceleration of the crate would now be less than the acceleration of the crate found in part A. Whew, so this is actually quite interesting. The reason is, obviously the acceleration is horizontal, isn't it? The horizontal forces here aren't changed. Look at the first one. The component of the horizontal force was 40 cos alpha. The 40 cos alpha was the thing pulling it. And in part B, the horizontal component of this force is 40 cos alpha again. So why would that change the acceleration? Horizontally, I'm getting pulled by exactly the same force. The difference is in the vertical plane. Last time, we had an up equals down. Now, in part A, look at what happened. The 40, the vertical component, was pulling it upwards. So in other words, I had R plus the vertical component of this force equals the weight. So in part A, the reaction force was the weight minus that vertical component of the tension. In other words, some value that was less than the weight. It was the weight minus something. So this thing is definitely some value less than the weight. That's part A. In part B, I do up equals down again, right? That's normal. And then I say, okay, well, now let's have a look at it. This component of this tension is actually going downwards now. So my up, I've just got the reaction. And then on the right-hand side, I've got the weight, as we did. But then I've also got the component of this force going downwards, right? I don't care exactly what it is right now, but I've got, that is pushing it, it's trying to take it down. So look at this. The R in part A was some number smaller than the weight. The R in part B is weight add a number. So this is definitely going to be greater than the weight. So the R in part B is greater than the R in part A. Now, why does that matter? Well, what's friction? Friction is mu times by R, right? So basically the friction in part B, mu's not changed, that's just the coefficient of friction, that's 0.14. The friction in part B is going to be greater than the friction in part A. So obviously, if I've got more friction, but the same force pulling it this way, well then it's not going to accelerate as quick, is it? So therefore, the resultant horizontal force is going to be less if there's more friction. So F equals ma, it's going to be less acceleration. So the friction is, resultant force to the right, so accelerating to the right will be less, therefore less acceleration. They ask this quite a lot. I see this a lot where it's like, you need to realize that this reaction force is going to change, therefore the friction changes, therefore the acceleration changes. Nice little question. Question 8, we're cracking on, and it looks like we have some more vectors. So, particle P moves with constant acceleration, right? Constant acceleration, the examiner is telling you, mate, use Suva equations. When A is given in terms of T, it's not constant, right? That is when we need to use calculus. We differentiate the velocity to get acceleration, differentiate displacement to get velocity, all of that stuff. When they are telling us, look, it's constant, Suva equations. The Suva equations are the equations of constant acceleration. So we're going to be setting up Suvas. Tan t equals 0, the particle is at O, some origin, and is moving with velocity 2i minus 3j. Tan t equals 2, so at the point A with position vector 7i minus 10j. Show that the magnitude of the acceleration of P is 2.5. Suva, straight in. So in this case, they're going to be vectors, so I'm just going to underline the vector quantities. So I'm going to get S, U, V, A, all vectors, and then T is just a scalar. Okay, what do we know? We know U, because it says the particle as its own is moving with velocity 2i minus 3j. Do we know V? No. Do we know A? No, that's what we want, right? Do we know T? We do, because that's 2 seconds. Now, S. The extra piece of information we have here is that at time t equals 2, it's at the point of position vector. Now, I'm here to tell you that you can use position vectors and displacement pretty much interchangeably. If you think of some, two-dimensional plane here, like we have here with the i's and j's, I've got some origin here, haven't I? And I say, okay, well, let's imagine I now move to some point, I don't know, 2i plus 3j, or whatever. The position of the particle is 2i plus 3j, but the displacement, well, how much have I displaced from the origin? Well, I've gone 2i and I've gone 3j, haven't I? So the position vector and the displacement, when they're just relative to this fixed origin of 0, 0, they're the same. So you might see kind of R maybe used in this if you look at kind of textbooks or something, and that would be, position, use whichever one you find easiest. So essentially, this S is going to be the position they give me. So that's going to be 7i minus 10j. So now it's just solve that equation time. We're allowed to use them in 2 dimensions too. So S equals ut plus a half at squared is what I want to use here. Now, this also works with vectors. In other words, S equals ut plus a half at squared. So I'm subbing in, I'm rearranging. So S is going to be 7i minus 10j equals u, which is 2i minus 3j. All of that's being multiplied by t, which is 2. And then plus a half a times t squared, so times 2 squared. I'm going to take all of this over to the other side because I want to isolate this term with the a in. So I'm going to get 7i. Why is my pen stop working? It is moaning at the mechanics. 7i minus 10j, and then minus 2 lots of 2i minus 3j, and all of that is going to equal what? Well, I get a half times 2 squared. 2 squared is 4. 4 times a half is 2. So I get 2 lots of a here. Clean up the left and see what we got, right? So how many i's am I going to have? I'm going to have 7i minus 2 times 2 lots of I. So that's going to be 7 minus 4, which is 3. And then I get minus 10j, minus 2 times minus 3. So minus 2 times minus 3 is positive 6. Minus 10 add 6 is going to be minus 4. And then all of that is 2a. Divide by 2 to get a equals 3 over 2 lots of I minus 2 lots of j. Is this the answer? Let's have a look. Show that the magnitude is not the answer. Because this is acceleration as a vector, I want the magnitude. So the acceleration is basically going 3 over 2 in the I direction, and then minus 2 or 2 down in the j direction. So the magnitude is just going to be the resultant of those. So in other words, I'm going to Pythag it, and I'm going to say that the magnitude of A is the square root of 3 over 2 squared plus 2 squared. I'm going to stick that into the calculator and hope that is the answer that they have. So I get 3 over 2 squared plus 2 squared all square rooted. Boom, 5 over 2, which is 2.5. Okay, one part done, halfway in. Right, let's see what part B has in store for us. Right, so at the instant when P leaves the point A, the acceleration of P changes so that P now moves with constant acceleration that. At the instant when P reaches point B, the direction of motion of P is northeast. Find the time it takes for P to travel from A to B. Right, there's a lot kicking off here. I think that's a lot harder than part A, but it's the same amount of marks. I think we're going to need to just kind of look at this from afar and say, right, what's kicking off here? What are the different sections of motion? I start out of O, don't know. I then go to A. I then go to B. And they're kind of two different sections of motion, aren't they? Because the acceleration changes. Okay, so here's the thing. We actually already know a lot of stuff about O to A because we just did a suvat on O to A in part A. So here's what I'm going to do. I'm going to grab this suvat here and I'm just going to put it down here because that is exactly the same thing. So this is the suvat for part A, isn't it? Nothing's changed. But we actually do know the acceleration here, don't we? We know that the acceleration is now what? It's 3 over 2i minus 2j. So we know more information, so that's easy enough. For part B, well, A to B, let's see what we know. So what I'm going to do is I'm going to just do same thing, suvat. See what we have. Do we know time? No. Well, that's kind of the thing that we're eventually going to want, isn't it? So that's kind of still an unknown. Acceleration, we do know that. That's going to be 4i plus 8.8j. V. Now, we don't know V, but they do tell us something. It says the direction of motion. So if you're ever thinking about kind of the direction of the motion, that's the velocity, isn't it? It's kind of the speed, velocity it's going. If it's traveling directly northeast, what's kicking off here? Directly northeast is, perfectly right in the middle there at 45 degrees. That must mean that my horizontal and my vertical are exactly the same. So if this is 45 degrees, then these two must be exactly the same. My I must be of exactly the same magnitude as J here, because, if J was bigger than I, it'd kind of be going up here, wouldn't be traveling northeast. If I was bigger than J, it'd be kind of going this way, wouldn't be traveling northeast. But if I was exactly equal, like right there at 45 degrees, it's traveling northeast, isn't it? So I think that is going to be the thing that we're going to need. So we don't know V, but we do know that, I is going to be equal to J here. Do we know anything else? Do we know S? I don't think it tells us anything about the displacement here, so no. Do we know U? We don't, but can we work it out? I mean, have a look at this. O to A, right? We know everything about that section. Isn't the final velocity of the first section just the initial velocity of the second section, right? The end of the first section is the same as the start of the second section. So those velocities are going to correspond. So I'm going to get this V, and I'm just going to inject it into this U here. So to get this V, what am I going to need? I'm going to do V equals U plus AT. I've got everything here, so it's quite easy. So what I'm going to do is I'm going to do V equals U plus AT. U is 2i minus 3j. A is this thing, and t is 2, so it's going to be plus 2 times that there. So 3 over 2i minus 2j. What am I going to get? Let's get my i's and my j's. I's, I've got 2 plus 2 times 3 over 2. J's, I've got minus 3 minus 2 times minus 2. So what have I got? 2 plus 2 times 3 over 2. Well, 2 times 3 over 2 is 3. So I've got 2 plus 3, which is going to be 5i. Again, my pen is moaning about all of this mechanics. How many j's? I've got minus 3 and then minus 2 times 2. For some reason, I seem to have 2 different minus signs there. I think that's just because my whiteboard's going a bit mad, but that should be that. So that's going to be minus 7. Okay, this I can now put straight in here, can't I? So this right here is going to be 5i minus 7j. Okay, now I've got enough information to work out the v for this second section of motion. So I'm going to do v, again, equals u plus at. Same thing. So what am I doing? U is now this v, so it's going to be 5i minus 7j. T is t, so I don't know. I'm going to keep that outside, and I do know the acceleration. That is 4i plus 8.8j. Group it all together. A ver lo que tenemos. So what we're going to do is we're going to put these i's together, and we're going to put the j's together. So we have 5 plus 4t lots of I, and we have minus 7 plus 8.8t lots of j. What happens here? Well, this is the bit where we use that northeast thing, isn't it? It's saying, okay, we've got some unknown, like t values and velocity here, but we do know that at B, so we know that at B, the I and the j must be equal. In other words, the 5 plus 4t must equal minus 7 plus 8.8t. This is an equation I can just solve. So I'm going to add 7 to both sides to get 12 plus 4t. And then I'm going to take 4t from both sides. Well, let's keep it here. Let's keep it here for now. And then on the next line, I don't want to go too over the top. So now I'm going to take 4t from both sides to get 12 equals 4.8t, right? Finally, I'm going to divide both sides by 4.8. to get 12 divided by 4.8, which is going to be 2.5 seconds. Whew, grim one, but we've got a couple more questions to go, so let's crack on with it. Question 9 looks like an absolute beast, so let's get it over with. It says a plank AB of mass M and length 2A rests with its end A against a rough vertical wall. The plank is held in a horizontal position by a rope. One end of the rope is attached to the plank at B and the other is attached to the wall at point C, which is vertically above A. First thing I want to mention, there's so many words. All I'm really doing is just describing what's in the diagram, right? So if you're ever thinking, how am I going to keep track of all this information? It's in a picture for you. So don't worry about this. That's why I'm kind of rushing through. Small block of mass 3M is placed on the plank at the point P where AP equals X, again, on the diagram. Plank is in equilibrium in a vertical plane, which is perpendicular to the wall. Fantastic. The angle between the rope and the plank is alpha. Ah, look at this. They're doing it again, where tan alpha is 3/4. Twice in one paper, they want you to realize, don't do the inverse tan to get alpha. Draw yourself a triangle. I'm going to go through this quickly now because I've literally done it in this paper before. That's how much they like it. Make your alpha, SOHCAHTOA, the classic, every time they do this. Okay, so that would be 3/4 because that's opposite of adjacent. Pythag makes that 5. Straight away, I know that my sine of alpha is going to be O/H, so 3/5. And cos alpha is going to be A/H, so 4/5. Always do that. I'm not even finished reading the question yet, but I just know that we need this. Put it in a box, leave it for later, right? And then later on, you can say, here's what I prepared earlier, boom, stick it in. You just always need to do it. Preliminary work, right? Fantastic. The plank is modelled as a uniform rod. That's good to know because it means the centre of mass is going straight in the centre. The block is modelled as a particle and the rope is modelled as a light, inextensible string. Ugh. Using the model, show that the tension in the rope is, wow, it's 5 mg times 3x plus A over 6a. Oh, that's grim, isn't it? All right. Here's the thing, right? Obviously, you're probably going to read it and you're going to be like, what? And you might freeze up and just get scared by it. If you think about it, obviously it's grim. We might not know exactly the way that we're going to get this exact answer, but we know the principles, right? We know, look, we've got a moments question. We know we're going to have to take moments. We know we're going to have to kind of get some forces on a diagram. We know we're going to have to maybe resolve some forces. So just get your equations in and then the answer's probably going to fall out. Don't worry too much about seeing that and just freezing up. We know what we know, so let's crack on with it. Let's get the diagram up. And we're just going to see what forces we can get on this. Tension is trying to keep this plank upwards and it always acts along the string. So tension is going to be like that. The centre of mass here is in the centre because it's uniform. In other words, kind of A away. So it's kind of going to be going down here. The weight of the plank itself, its mass is big M. So I've got mg going downwards. The mass of this block is 3m, so I've got 3mg going downwards here. Now, A is always a tough one, so let's have a think. Basically, we're going to have vertical and horizontal forces at A. The first thing is it's definitely going to have a horizontal component because, it's pushing the plank this way. So there is going to be some horizontal component. And then, it's whatever you want to call it. You could maybe call this like RH for like the horizontal component of the R. And it is actually also going to have some vertical component. So let's have a think about it. What direction do we think this will be moving in? Ask yourself this. If the wall just instantly disappeared, what direction would this fall in? And I think it would kind of fall, obviously it's going to go this way, which is why horizontally it's taking it that way. And I think it would fall downwards, wouldn't it? This is kind of just going to come down here and fall down. Meaning that if it wants to go down if the wall wasn't there, what the wall is doing is the wall is keeping it up. So that's our vertical. It's a tough one there. It is a tough one. Luckily in part A, I don't think we need to concern ourselves with these. This is why. I'm going to take moments about part A here. Now this is a really useful technique. There are loads of unknowns in this equation, right? Think about moments. A moment is force times distance, and we can choose a pivot point. If I choose a pivot point at A, what would be the moment from these? I would take, the force, right, RV or whatever, times by the distance of the force from the pivot point. Well, the force is at the pivot point, so the distance is 0. So I'd get RV multiplied by 0, and all of these forces are cancelled out. So if I ever want, if I want to get rid of an unknown from an equation, I'll just take moments about the point where that force acts, and then it won't be there. So I'm going to take moments about A, and I'm basically going to balance everything trying to take it, kind of rotate it one way like this, is going to be balanced by everything trying to rotate it the other way. So everything trying to rotate it clockwise, it's going to be these two, isn't it? If I held this at A, these two forces are trying to pull it down like that way, and then the tension's trying to rotate it the other way. So I'm going to get the moments from these two lines on the left-hand side. So the first one is going to be force, which is mg, times by the distance. Well, remember, this is going right in the middle. Whole length is 2a, so this distance is just a. Plus x, which is the distance, times 3mg, which is the force. We'll put that 3 outside, and I'll get that. This is all going to be balanced by this tension here. And what way is that tension trying to act it? So I need the vertical component of this tension here. So I need to go away from the angle. So it's sine. So that's going to be T sine alpha. Okay, so I've got an equation here. I think I'm ready to just rearrange and see what happens. I am not, am I? Because I missed something out. T sine alpha is the vertical component of the force. But that's not the full moment, is it? Because the moment, I need to multiply by the distance from the pivot point as well. So that's T sine alpha times 2a. See, everyone makes mistakes, but you just got to find them. Okay, so I think at this point, I should be okay. So the first thing is that I know that sine alpha is 3/5. So straight away, I've got 2a times t times 3/5, which is going to equal what? So that's going to be 6a over 5 times t. I'm now going to multiply both sides by 5, divide both sides by 6a, and that's going to get me the tension on its own. So multiply by 5, so I'm going to get 5 times by mga plus 3xmg, and then divided by 6a. Okay, so tension is going to equal what? Can I take anything else out of this bracket? I think I can. They've both got big M's. They've both got G's as well, and I think that's it. So I'm going to take, the 5 is already outside. I'll take an mg out, and what am I left with? Here I've got an a, and then here I've got 3x. Now I hope this is what they are actually. It's over 6a, and they want 5mg, sweet, times 3x plus a plus 3x, same thing, divided by 6a. Sick. Okay, so that is part A. I'm surprised that actually came out that nicely, to be honest with you, but there we go. Part B. So it says, oh, here we go. Okay, so we're now getting told about this kind of reaction. The magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2mg. Find x in terms of A. Okay. We now know that this RH is 2mg. Why don't I even just get it in my diagram? So here I have a 2mg, which is good because I've done moments, but there are two more things that apply here. Left equals right and up equals down. So I'm going to do left equals right here because this thing is completely horizontal. The only two forces that act horizontally are this 2mg and then the horizontal component of the tension, and they act the other way. So they're going to balance each other out. So I'm going to get 2mg equals t cos alpha here. 2mg equals t cos alpha. I know what cos alpha is. I believe it's 4/5. So t. Now, what I am going to need to do is sub in all of this. So let's just get that over with. So I'm going to have 5mg a plus 3x, I know, over 6a, and then times by the 4/5 from the cos alpha. And then all of that is equal to 2mg. Okay, so let's see what we can simplify. I mean, the first thing I'm looking at is mg's are going, aren't they? Which is good. Anything else I can do? Let's just carry on. So now what I'm going to do is I'm going to multiply. Let's multiply up by this 6a. I'll leave the 4/5 there for now. So I'm going to have 2 times 6a, which is going to be 12a. This is going to equal, the mg's are gone, remember, so 5 times by a plus 3x, then I've still got this 4/5 there. Okay, look at these. These 5s cancel, which is good. So straight away, I'm just going to get 4 now times a plus 3x equals 12a. And what do I want? I assume I want x in terms of a, right? Yeah, perfect. Okay, I'm going to multiply this 4 out to get 4a plus 12x. I'm going to take the 4a from both sides, so I'm going to get 8a equals 12x, and x equals 8a over 12. I can cancel this a bit, can't I? I can divide both top and bottom by 4, so I'm going to get 2a over 3a. Hope that's right, but it seems right. Okay, that's 2 bits. I've got 2 more to go. Okay, so the force exerted on the plank at A by the wall acts in a direction which makes an angle beta with the horizontal. Find the value of tan beta. Woo! Okay. Now, I've got 2 forces here, haven't I? You know, it's kind of got like a horizontal component and a vertical component. So all together, that kind of makes a force, you know, it's got a resultant like that, hasn't it? So what it's saying is this here is beta. And we want the value of tan beta. Again, I have no idea how I'm going to get tan beta, but I do know that, you know, normal equations apply here, right? So this is what we're always thinking about. We're just saying, look, I've got a moments question. I know that at some point I'm going to have to take moments. At some point I'm going to have to do a left equals right, and at some point I'm going to have to do an up equals down. They could ask me anything here. I would just think, what have I not done yet? I've not done an up equals down, have I? So without even caring about the tan or anything yet, I'm just going to say, look, let's do an up equals down, see what happens. So there's a few things going up here, isn't there? There's this vertical component, RV, and there's the vertical component of that tension. So going up, I've got the RV plus T sine alpha. So let's get that here. This is part C. I've got the RV plus T sine alpha going upwards. Going downwards, what do I have? I have mg and then the 3mg, right? So that's actually just going to be 4mg. I know, we are getting there, but hopefully I don't even know if we're getting there. Right, okay. So what am I doing? I want tan beta. All right. Obviously, I know T and I know sine alpha. So I'm going to put all of those together. I also know X in terms of A. So I think everything here should get nice here. So I'm just going to sub everything in and see if anything simplifies. So RV, I'm going to get RV on its own because I think that's going to be important here. So it's going to be 4mg minus, okay, so sine alpha is 3 over 5. So I've got 3t over 5 here. Okay, here we go. 4mg minus 3 over 5 lots of t. Now t, if we recall, is this 5mg times 3. So it's 3x plus a, but we know what x is now. So I think we should, stick that in. So that's going to be 2a over 3. And then plus another lot of a. Make sure all the brackets are here. Yeah, and then it's all divided by 6a, isn't it? Okay, now this might look scary, but I actually think quite a lot of stuff's going to cancel out here. So let's keep this 4mg here. Now, let's keep the 3 over 5 here as well, and just work out this first of all. So I'm going to keep the 5mg here. There's about 4 layers of brackets here. 3 times 2a over 3. The 3's cancel and I get 2a. And then I get 2a plus a, so that's going to be 3a divided by the 6a. Okay, now I think some nice stuff happens. 3a, 6a, a's cancel. And then, I can cancel the numbers quite nicely as well. 5's also cancel, by the way. So I'm kind of getting there now. So what am I left with? I'm left with 4mg minus, I've still got a 3 here. 5's gone. I've got mg. This a's gone. I've got a 3 here. And I've got a 6 here still. So we're slowly getting there. This is going to be 9 over 6 lots of mg, isn't it? So I can take an mg out. I've got 4 lots here. And then minus 9 over 6 here. Right. Okay, what's 4 minus 9 over 6? I cannot be bothered to work that out in my head because I don't have to. So that's going to be 5 over 2. So I'm going to get 5 mg over 2 here. Okay, let's catch up with ourselves. What have I just shown? The vertical component of this thing is 5 mg over 2. Okay, let's actually kind of deep dive into this force. Okay, I know I've got a vertical component here, 5 mg over 2. I've also got a horizontal component, which, by the way, I do know, don't I? Because they told me that. So that horizontal component is going to be, which they did tell me, is 2 mg, okay? So what I've got here is I've got 2 mg here, 5 mg over 2 here. Oh, here we go. I get it. And then look, the resultant is this, isn't it? The angle is beta. Oh, what a question. Like, so the angle is beta. So now I'll say, okay, well, how do I get tan beta in a triangle? What do? I say that tan beta from SOHCAHTOA is equal to opposite of adjacent. So the opposite is 5 mg over 2. Divided by 2 mg. Okay, so what's this going to be? The mg's have gone, aren't they? So I've got 5 over 2 divided by 2, which is going to be 5 over 4. And I believe that that is going to be tan beta. Wow, that was very hard. I'm not going to be mad at anyone for not getting that. Okay, last part here. So it says the rope will break if the tension in it exceeds 5 mg. Explain how this will restrict the possible positions of P. You must justify your answer carefully. We've got to be careful here, apparently. Okay, so possible positions of P. Okay, well, tension 5 mg. So, well, we know what tension is, don't we? We've had this, expression for tension this whole time, haven't we? Which is basically what we derived in A, which is 5 mg times 3x plus A all over 6A. And we're now told that this cannot exceed 5 mg. So it has to be less than or equal to 5 mg. And this is nice. Why? Because what's been happening the whole time? Mg's have been cancelling. 5's have been cancelling. This goes to 3x plus A. Don't even need a bracket anymore, to be completely honest with you. Over 6A. Has to be less than 1 now, because I've cancelled 5 mg. So I want something that restricts the positions of P. The position of P is to do with x, isn't it? Because x is the distance from A of P. So if I can get something here with x in, which I can, I'm going to multiply by 6A. Don't need to worry about the sign flipping because I know A is positive because it's a length. So this is going to be 6A. I'm going to take A from both sides to get 3x is less than or equal to 5A. And then I'm going to divide by 3 to get x is less than or equal to 5A over 3. So what is happening now? I want to know, look, we'll restrict the possible positions of P. So if you think about it, I know that x must be less than 5A over 3. And I think, what is x? So really, I must say, let's put it into words. I would say, P must remain a distance from A, because that's what x is, isn't it? It's the distance from big A to P. Must remain a distance from A, less than or equal to 5A over 3. And I think that is, that is my restriction, isn't it? If P is further than that, tension is breaking. All right, that question was horrible. And I've only got one more, so let's just get through this one and we are done. Boss fight. A boy throws a ball at a target. At the instant when the ball leaves the boy's hand at the point A, the ball is 2 meters above horizontal ground and is moving with speed u at angle alpha above the horizontal. In the subsequent motion, the highest point reached by the ball is 3 meters above the ground. The target is modelled as being the point T, as shown in figure 4. The ball is modelled as a particle moving freely under gravity. Using the model, show that u squared equals 2g over sine squared alpha. Right, projectiles. All you need to master is you need to do a horizontal suvat and a vertical suvat. And these two things are just completely independent because, the horizontal and the vertical motion, they don't care about each other. So we're going to have to use something like that here. What I'm thinking is the following. To get the horizontal and vertical components of this initial velocity, we resolve. Now, if I was to get the vertical, I'd be going away from that angle, and it would be u sine alpha. Look at the answer, it's got sines in it. So I'm thinking that the relevant suvat that I'm going to need here is the vertical one. So let's get this down. So if I suvat on the vertical, what am I going to get? Now, the piece of information that I want to use here is its maximum height, because I know a couple of things. I know that at its maximum height, just for that instantaneous moment, the vertical velocity is 0. It's not going up, it's not going down, it's just going like that. So v is going to be 0. I know that s, it's not 3, is it? Because it's 3 meters above the ground, but I start at 2. So I've gone up, I've been vertically displaced by 1. So s is going to be 1. U, as I said, is going to be this u sine alpha. Do we know anything else? We do. We know that acceleration is going to be due to gravity, but think about it. Gravity is always trying to pull you down. So it's not going to be g, it's going to be minus g. What relates these two things? I believe it's v squared equals u squared plus 2as. So I'm just going to sub everything in. V squared is 0 squared, which is 0. U squared is going to be u squared sine squared alpha plus 2as. So a is minus g, so it's going to be minus 2g, and then s is 1. Take the 2g over the other side. I'm going to get 2g equals u squared sine squared alpha. And I'm going to divide by sine squared alpha. And it looks like straight in I've got this 2g over sine squared alpha. Cool. Right. Oh my god. This is worth 9 marks. Right. Let's go. Just get a cup of tea. Get ready. We're going in. The point T is at a horizontal distance 20 meters from A and is at a height of 0.75 above the ground. The ball reaches T without hitting the ground. Okay. Find the size of the angle algebra. Again, I wouldn't expect anyone to have this kind of tunnel vision of exactly how they're going to get alpha from this. But what I would expect you to do is to know, look, I'm in a projectiles question, I'm going to need a vertical suvat and a horizontal suvat. I don't care about what the last lines are going to be and specifically what I want. I just care about, look, I know how to start this. Everyone does. Okay, so I'm going to do suvat. Now, instead of doing it to the top point here, because I've already kind of cached that bit of information, I'm going to do it to the point T. So vertically, what are the suvat variables from A to T? Displacement. T is 0.75 meters above the ground. But remember, A is 2 meters above the ground. So if I have A here, and this is 2, and then T is here, and this is 0.75, well, the amount I actually displace from A to T vertically is minus 1.25, isn't it? So S is going to be minus 1.25 here. U is going to be U sine alpha. We know that. That's the initial. V, we don't know. No idea. A, same thing. It's going to be minus G. T, we don't know. But I'm going to call this T. Just going to get rid of this. Horizontal. What have we got? Suvat. Okay. Horizontally, we actually do know. We're told that it's 20 meters away. So I'm going to get a 20 here. U is now going to be the horizontal component, which is U cos alpha. V, no idea. A, there's actually no acceleration horizontally. Gravity acts downwards. The horizontal direction does not care about that. So this is actually going to be 0. And then T, this is the only thing that they share. They do have the same time because time is just the same. At point T, you know, they both, obviously the horizontal and vertical, they have this same time. So that is what's shared. And this tends to be the link between these two equations. What I can do now is just you do some suvats, right? There's loads of unknowns flying about. If I'm clever with the algebra, I think I'm going to be able to do this. So S equals UT plus a half AT squared is what I'm going to use for both of these, because this is the one that has no V's in it. Vertically, I'm going to get minus 1.25 equals U sine alpha times T, so TU sine alpha, plus a half AT squared. A is minus G, so I'm going to say minus a half G and then T squared. That looks good. Horizontally, I get what? I get 20. Let's do a little separation of these. Horizontally, I get 20 equals U cos alpha times t, and then plus a half at squared, but a is 0. So it's actually just that. This is good. Okay, look at what's shared between these things. It's the t, isn't it? If I rearrange the simple equation to get t, I think I'm going to be able to chuck it into that left. So t here is going to be 20 divided by u cos alpha. I'm going to chuck that in here, and then hopefully nice things happen. Okay. Minus 1.25 equals 20 divided by u cos alpha. That's the t. And then times by u sine alpha minus a half g t, which is 20 over u cos alpha squared. All right, it's kicking off. But this is nice. Look at these. These u's cancel. Sine over cos is tan, so I get 20 tan alpha here. What do I get here? Minus a half g. 20 squared is 400. So these are times 400, and then over u squared cos squared alpha. Right then, what do I do now? So I've got alphas, and that's the thing that I want, but there's still another one known here, and that's the u. Can we think of anything to sub in for this u? Well, what did we do in part A? Part A told us that u squared is equal to 2g over sine squared alpha. In other words, this thing here is about to get messy, so let's just be really careful. Make sure we're checking our work here. First thing I'm going to do, you know what? I've got 400 and I've got a half, so I'm just going to mush them together and then I'll get 200. So I'm going to get 200g on the top here. That's these three terms. Divided by, okay, u squared is 2g over sine squared alpha. And then I've still got this cos alpha here. Cos squared alpha. Okay, it looks grim, but I actually think this is okay. Because this is going to be 20 tan alpha. Okay, I'm just going to actually just write a division sign so we can really see what's going on here. So I've got 200g essentially just divided by this. So it's 2g cos squared alpha divided by sine squared alpha. I know there's a lot going on, but just step by step. In each single step, we're not doing anything crazy. Now, if I divide by a fraction, that's the same as multiplying by that fraction flipped, isn't it? Meaning that this is going to be 200g multiplied by sine squared over 2g cos squared. Now, this is good, isn't it? Because isn't sine squared over cos squared tan squared? We've already got a tan here, so I'm going to get minus 200g tan squared alpha over 2g. We are getting there. Okay, I've got another nice cancellation to do, haven't I? So I'm going to get 20 tan alpha minus g's cancel. 200 divided by 2 is 100, so I get minus 100 tan squared alpha. And remember that all of this is equal to minus 1.25. Now, we have a quadratic, don't we? Get it all onto one side. 100 tan squared alpha. I'm going to put it onto that side. So minus 20 tan alpha minus 1.25 equals 0. Wow. Now, this is a quadratic in tan alpha. So if, for example, I was to let y equals tan alpha, what am I going to get? I'm going to get 100y squared minus 20y minus 1.25 equals 0. Now, I could try and be clever and factorize, but who cares? So I'm actually just going to stick this into my calculator. What I can do is I can find the equation, wherever it is, equation function. I'm going to put in a polynomial because that's what it is. The degree, so basically the highest power, it's a quadratic, so the degree is going to be 2. And now what I can do is I can put in each coefficient here. So the 100 in front of the x squared, the minus 20 in front of the x, and the minus 1.25 in front of this on the end. So my first solution for y is a quarter. My second solution for y is minus 1 over 20. Now they look quite nice. I'm not quite done yet though, are they? Because these are values of tan. So I have tan alpha being equal to 1/4 or minus 1 over 20. Now, super quick, the tan graph, I'm just going to give you one little chunk of it here. It's going to correspond to this. The reason I'm giving you this chunk is because, look, we know from the graph that alpha is between 0 and 90, right? It's just an acute angle. It's not negative, any of that. This is 90 here on the tan graph, meaning that I don't need to do more than that because I know my solution is going to come from here. Now, 1/4 is kind of here, and then minus 1 over 20 is here. So minus 1 over 20 is not going to give me any solutions, is it? Because minus 1 over 20 is going to give me a solution here, which is a negative value. The one that I want is this one that corresponds to 1/4 because they intersect here. So if I do the inverse tan of 1/4, making sure my calculator is in degrees, I'm going to get my value of alpha. So alpha is going to be the inverse tan of 1/4 because I can discount this one, don't care, it'll give me a negative angle to get me. So my calculator is currently in radians, so I'm going to quickly swap that over to degrees. Always check to get the inverse tan of 1 over 4, and I get that as 14.01 degrees. 9 marks, big one. We're not quite done, are we? Okay. State one limitation of the model that could affect your answer to part B. Loads of things. The classic one that I like to go for is that this has no air resistance in the model. So in reality, there is air resistance, right? And air resistance matters a lot. I said that there's no acceleration horizontally. It's probably not really going to be true because as my thing is, flying through the air is slightly pushing back on it. So I think it's actually going to kind of slow it down a bit horizontally. So basically, yeah, these models that we do in mechanics and A-level, they don't have air resistance in them. Find the time taken for the ball to travel from A to T. Okay, so I think we've done the hard graph here now. That's not B, by the way, that's C. We've done the hard graph. We just need to find the time, but I think we've got a lot of equations here. So first thing I'm thinking is I can get U, can't I? Because U squared is 2G over sine squared alpha. So if I get U here, I can then substitute into one of the equations I got in part B to get the time. So U is going to be the square root of 2G over sine squared. And we know alpha is this. So what I'm going to do is I'm going to go to my calculator. Now remember, I've got alpha already saved as an answer, so I don't need to worry about rounding errors here. So I'm going to do the square root of 2 times 9.8 divided by sine of answer, and then that squared. So that right there, making sure my brackets are good. I seem to be getting, you know what, there is an exact form, so I'm going to keep it there because I'm going to use it in a future calculation. I get 7 times the square root of 170 over 5. Let's look and just let's crawl through our equations and see if we can find anything that will give us the time here. I think that I would like to use this. I know I had a simple one with a horizontal equation, didn't I? 20 over U cos alpha. I'm going to use that. T equals 20 over U cos alpha. So to finalize this paper, finally, I'm going to do T equals 20 over U cos alpha, which is equal to, basically, I'm just going to sub everything in. So get to my calculator. Now, the U is saved as an ants, which is fantastic. Alpha, I'm going to use that. So I'm going to do 20 divided by ants times by cos, and then a 14.01. And I get the time to be 1 point, let's go three significant figures here, 1.13 seconds. Always think with the mechanics when you get a real number at the end, think does it make sense? 1.13 seems quite small, but then again, projectiles, it happens very fast. What we do when I'm throwing a ball, chuck a ball, in a second it moves quite far. So I think that I can finally finalize this paper like that. Well done, that was absolutely horrible. Both the questions and listening to me go on for probably what's going to be about a 2-hour video. Best of luck with it, and let's crack on.